Hello and welcome back to the second part of the dot product lesson. And in this part, we will focus on the concept of the unit vector. So what is a unit vector? To start with, a unit vector of some vector v is indicated by the same letter v, but then we use a different symbol for the unit vector, which is in the form of this tiny little hat on top of it. Now, very often it's being, overlooked at, and sometimes for the unit vectors, a simple arrow is used. Now, a unit vector has a magnitude of 1 unit, and it has the same direction as the vector itself. The formula for the unit vector may seem a little bit complicated at first, so let's break this down a little bit. So I'm going to draw in here some vector, and we're going to call this vector v, since we were talking about vector v. And we're going to give vector v, say for example, 5 units, which means that, 5 units in length, which means that if I divided this this vector or line that represents a vector into 5 equal parts, then each part of it will be 1 unit of the vector v. Okay. In other words, so this one here, this vector here, will represent the unit vector v. Now let's talk a little bit about the size of this vector. We're going to say that the unit vector v in length will be 1/5, because there are fifth parts equal to vector v here, right? So 1/5 of vector v itself. So we're going to write this down, 1/5 of v. And now we're thinking, wait a second, number 5, how else can you describe it? So we're going to say 5 is actually the magnitude of vector v. So instead of number 5, I will write magnitude of v here. Also recall that whenever we use the word of in different mathematical statements, the operation behind it is multiplication. So we'll say that we have 1 divided by magnitude of v of vector v, or multiplied by v. And obviously you can see here that we have 1 over a number multiplied, so a fraction multiplied by another term, which means that we're multiplying the tops together, the bottoms together, and this can also be written as v divided by the magnitude of v. And this is the formula for the unit vector, and that's what we looked at here before. Now, this is my more favorite, my preferred way of describing unit vector v is as a ratio of vector v divided by its magnitude. Remember that v is a vector, right? So not only it has 1 unit, but it will follow the direction of v. And having v in the numerator gives the unit vector v the vector properties. Now let's take a look at an example and see how we can find the unit vector of a given one. So here we have vector a. Vector a is an algebraic vector described by the coordinates x equals 7, y equals 24. So to find the unit vector of a, or in other words, this little a with a hat, means that we have to use the formula vector a divided by its magnitude. So vector a itself has the coordinates 7, 25, 24. This is how we can describe vector a, right? Divided by the magnitude, and for the magnitude we have to do a little bit of work. Knowing the coordinates of vector a, we can say the magnitude of it will be the square root of 7 squared plus 24 squared, which is square root of 625. That will give 25 units. So that means that unit vector a is 7, 24 divided by 25. Now, since a, the unit vector a, is a vector, then we'll describe or we'll determine the coordinates based on this formula. And we'll say that unit vector a equals 7 over 24, 24 over 25, 24 over 25. Because basically what you're seeing here actually is when you divide by 25, it means that we're taking 1 over 25 of, or 1/25 of vector 724. So you're multiplying the vector 724 by this scalar, right? The magnitude is 25, and the unit will be 1 of the 25 unit length of the whole vector that is described by these coordinates. Now, how does this really work geometrically or visually, let's say? So in order to better understand this, what I'm going to do is bring an example, a very simple example with a vector on the Cartesian plane. And this time I'm going to choose the vector with coordinates 3 and 4. So here is 3. I like 3 and 4 obviously because they are they make the Pythagorean triple 3, 4, 5. So it makes the calculations easier, and it makes the point clearer and faster, whatever we're trying to prove. So here is our vector. Vector OA, let's call it for now. Here we go. So we're going to say that this vector here, I'm going to call it by letter A actually. So vector A will have the magnitude equal to square root of 3 squared plus 4 squared, so that would equal 5. So we're going to say that vector A is 5 units. So let's divide this into 5 equal parts. So let's see. 2, oh, that's not perfect. So let's try this. 1, 2, 3, 4, 5. So I divided vector A into 5 parts because I want to see how big each part is. So this would be the unit, 1 unit of vector A. So in other words, this would be the little a with a hat. So if you look at the coordinates of the little a here, you can tell that the coordinates, the x component and the y component of this will be less than 1. And you can tell that 7 over 25 obviously is less than 1, and 24 over 25 is less than 1. And again, the scaling is not perfect, but the idea should be there. And this makes sense in another way if you look at it, because if you dropped perpendiculars for every unit vector here, because look at how many unit vectors we can draw. So there's another one, here is another one, here is another one, right? And here is another one. So there is 5 A's in here. So the x coordinate is shared, right, into 5 parts. So therefore, we're going to say that the x coordinate will be 3/5, right? And the y coordinate of the unit vector will be 4 over 5, right? Because here we go. So we're going to say unit vector A equals 3, 4 divided by the magnitude, which is 5. So 1/5 of vector 3, 4, which is going to be 3/5 and 3/4. And you can tell that the coordinates here are 3/5 and 3/4, so they're below 1. Now, in the next concept that we're looking at are projections. So what are projections? Now, for now, we're going to take a look at the diagram and try to derive all the formulas on our own. Here we have 2 vectors, vector B, vector A, placed tail to tail and making an angle theta with each other. We're going to say that the projection of vector A onto vector B is indicated by this symbol. So we write projections, P or PROJ for short. We write vector A first and vector B at the bottom here, which tells us that this is the vector we are projecting and this is the vector we are projecting on. The projection is drawn by dropping a perpendicular from the head of the vector we are projecting onto the vector we are projecting on. And this will be what we call the projection of A onto B. The projection of A onto B, as you can see, is a vector on its own, and it follows the direction of vector B. It will have a magnitude that varies based on the position and the size of vector A. So remember, for example, if we were to change, for example, the position of vector A, here we go, I'm going to do something different. So for example, we have some vector A. So if the angle increases, the projection, try to imagine it, will change as well. Or I'm going to take actually exactly this one. So the same vector, if we change the angle, the projection will become bigger to a maximum of A units. And if the angle changes, obviously, the projection will get smaller. So we are going to talk about both the magnitude and the direction of the projection vector. We'll start off with the magnitude. We're going to say that the magnitude of the projection of A onto B will be located adjacent to angle theta. In this triangle, we have a right angle triangle, so we have this right angle, and this will be vector A with a magnitude A. So we're going to say that adjacent over hypotenuse will give cosine theta. So in other words, we'll say projection of A onto B divided by the magnitude of A will equal cosine theta. This will make the magnitude of the projection of A onto B equal to magnitude of A times cosine angle theta. And we're talking about just the magnitude for now. And now we're thinking, okay, so we got the magnitude, but how about the vector value of the projection? So we said that this vector will have the direction of vector B. So it makes sense to say that to follow the direction of B, we have to multiply by the unit vector B. So I'll write down here unit vector B. I'll make this green as well, just to connect them. Now recall that unit vector B, on the other hand, can be written as, so here we go, cos theta. Unit vector B is vector B divided by the magnitude of vector B. Now, to make things more interesting so that we find more connections between the projection and the dot product that we just learned, so we're going to do something fancy here. So we'll multiply both numerator and denominator, or the whole expression, by B over B, which is practically multiplying by number 1, because it's the magnitude of B divided by magnitude of B is 1. And here is the reason why we want to do this. You see that here we have A, we have cos theta, and we have B. So magnitude of A, magnitude of cos theta, magnitude of B and cos theta will give together A dot B. On the other hand, we have B and B multiplying each other, so they will stay in the denominator. And obviously, when you have the magnitude of vector B times itself, that would be magnitude of vector B squared. Or another way of looking at it would be magnitude of B times magnitude of B. Think of the angle that B makes with itself, which is cosine, which is angle 0, which means that we can easily add in here a cosine of 0, right? So if you have magnitude B, cosine 0, that's the dot product of B with itself. So the only term that hasn't been involved so far would now be the vector B. So we'll say that the projection of A onto B is A dot B divided by B dot B times the vector B itself. So let's take a look at an example. And this is all described in here, but it's nicer when we derive the formula on our own. So we're going to take a look at the vector projection of OA onto OB. So we're trying to project vector OA onto OB. There are two algebraic vectors, and we're going to say that if you want to find the projection of vector OA onto OB, OA will stay on top here, OB at the bottom of the word projection, that would equal the dot product of OA with OB divided by the dot product of the vector where we're projecting on over the times dot with itself, OB dot OB, and then times the vector OB. Now, one thing that I want to actually emphasize here, remember this is dot product, and we want to make this dot very pronounced to indicate that it's not an ordinary multiplication. And this one here, I'm just going to leave it as multiplied. Now let's multiply or dot product these vectors. So we know how to do this. So we have 4 and negative 3, that's OA, dot 5 and 4 over, down here we have 5 and 4 dotting itself, multiplying itself, right? And then here we have the vector 5, 4, vector OB. So again, the same drill, 4 and 5, so X is together, Y is together. X is together, Y is together, and you add them, right? So 4 times 5, 20, plus 4 times negative 3, negative 12, over 5 times 5, 25, plus 4 times 4, 16, times vector 5, comma 4. All right, so remember again, 4 times 5, 4 times negative 3, right? And 5 times 5, 4 times 4. So simplify, so 20 plus negative 12, that's an 8. 25 plus 16, that's 41. And then 5, 4. Which means that the projection will be 8/41 of the vector 5, 4. So multiply 8 times 5, that would be 40 over 41, comma, 8 times 4, 32 over 41. So these will be the coordinates of the projection of vector OA onto vector OB. So why don't we take a look at these two vectors on the Cartesian plane and see how exactly did this happen? So how did we get these coordinates for the projection? Does it really work? So here we go. We're going to draw the vector OA. Coordinates of OA are 4 and negative 3. So it seems that vector OA is right here. Now we have vector OB with coordinates x5 and y4. So that would be right here. So I will call this B and this one is A, and I'll draw the arrows to make this look nice and pretty. Okay. Now, I want you to imagine that in this case, we're trying to draw the projection of vector OA onto OB. I'm sorry the grid is not very clear because these are PDF documents and they don't look very good on GoodNotes when you have pictures PDF'd. So to draw the projection of OA onto OB is drawn by dropping perpendicular from A onto OB. So I'm going to try my best to draw a perpendicular here. Obviously it's eyeballing a little bit, but the idea should be there. So if you drop the perpendicular here onto OB, then you would see that the leg of the perpendicular would be right here at this point. This will mark the projected vector. or the vector projection of OA onto OB. As you can see here, the coordinates are kind of clear here. So less than 1 and less than 1 for both x and y. And you can tell that 40 over 41, so the x coordinate seems to be a little bit bigger, and 32 over 41. So, and you can tell that the x coordinate is closer to 1 and the y coordinate is a little bit further than 1 here. And that's how it works. It's like magic almost. Next, we're going to take a look at example number 7. In example 7, we have to find the acute angles between the diagonals of a rectangle with sides 5 and 8 centimeters. So we are told that this length is 5 and this length here is 8. So the diagonals that of this rectangle would be drawn by connecting the opposite vertices. And I'm going to use different colors for them, and I'm going to call them by the names D1 and D2. This is diagonal D1 and this is D2. And for ease in calculations, I'm going to place this rectangle on the Cartesian plane. Here is my fancy Cartesian plane. And here is the x-axis. And in this way, I can interpret the information about the measurements of this rectangle differently and enrich the information in some way. So here we go. We have this point here. This should have the coordinates x equals 8 and y equals 0. Now, this point right here will have the coordinates x equals 8, y equals 5. This one here would be 0 and 5. And here we go, 0, 0. Now, the acute angle between the diagonals will be this angle here. And I am going to give diagonals a direction. So here's the diagonal D1, and this one is D2. And to find the angle between the diagonals, I'm going to place them tail to tail. So here we go. I am going to bring the diagonal D2 with the tail at the origin. So now they are placed tail to tail. So this angle theta, the acute angle, that's what we're looking for, is the same as this angle theta. Why? Because these two are parallel to each other. It's the same vector. You translate a vector everywhere. It stays collinear or parallel to itself. So in order to find the angle made between the two diagonals, so this angle here, we need to find the angle made between these two vectors. So we're going to say that D1 dot D2, remember how we said dot product is great at helping us find angles, would be magnitude of D1, magnitude of D2, cosine of the angle between them. Now recall that D1, the magnitude of D1, will be the square root of its coordinates. So that would be 8 squared plus 5 squared. 64 plus 25, and that would equal 89, root of 89. I'll leave it as is. For the diagonal D2, obviously the magnitude is the same because they're the diagonals of the rectangle, but if you want to go the more analytical way, then you will go ahead and define the coordinates, which will be in this case x equals 8, y negative 5. So we're going to say that D2 will have the magnitude square root of 8 squared plus negative 5 squared. So that would be again root of 89. Now D1 dot D2 would be 8 and 5 dot 8 negative 5. So we have 8 times 8 plus 5 times negative 5. So that would be 64 minus 25. And 64 minus 25 will give 39. So the dot product D1, D2, so that's the algebraic dot product, equals 39. So let's put all these numbers to work. Again, this is the formula that we are using. That's highlighted. So we'll say that d1 dot d2, which we now know is 39, equals magnitude of d1 root 89, magnitude of d2 root 89, cosine of the angle that we don't know. So 39 equals 89 cos theta. Divide both sides by 89 to isolate cos theta, and we get theta equal to inverse cos 39 over 89. And inverse cos 39 over 89 will give the angle 64 degrees. And voila, it's an acute angle, right, made between the two diagonals. Now, obviously, you could have found the angle between the diagonals using other methods, like more geometry methods. You can use them, or trigonometry, like simple trigonometry, and you can use the simple trigonometry actually to figure out this angle and just to check if your dot product formula worked. The last example. We're going to use the dot product to solve a problem involving perpendicular vectors. We are given two vectors. They're called A and B. And as you can see, for A, we have all three coordinates. For B, we are missing the coordinate K, which is the Y. We're told that the two vectors are perpendicular, so we want to figure out what K value will make sure that they are perpendicular. So we're going to say if they're perpendicular, then you're telling us that A dot B is 0, which means that 1 times 3 plus 3 times K plus negative 4 times negative 2 equals 0. So 3 plus 3K plus 8 equals 0, or 3K equals negative 11, K equals negative 11 over 3. That's the K value that will guarantee that these two vectors are perpendicular. Now, the next example is for you to try. It's very similar, slightly different, obviously. Again, the two vectors are perpendicular. This time we're missing the variable m, which appears in more than one spot. The idea or the concept is the same. So we're going to use again the dot product u dot v, which is going to be 0. So you multiply the x coordinates, m times m, that's m squared. And then we multiply the y coordinates, m times negative 3, so that's negative 3m. And last but not least, the z coordinates, 3 times 6. So that would be minus 18. And that must be equal to 0, we said. Now we have to solve for m. As you can see, this is a quadratic equation. So we go m minus 6, m plus 3, make each factor equal to 0, and m plus 3 equals 0. And from here, we're going to say that m equals 6 or m equals negative 3. And in this case, we found two possible values of m that can make the two vectors perpendicular to each other. So there are a couple of thinking questions that I really want you to try on your own, and we'll discuss them in class the next day. Well, I hope that you're enjoying learning vectors. They're fascinating and they require a little bit of patience and organizing the information in your head. Just keep working, do your work every day, practice questions every day, and you will find this even more enjoyable. Thank you very much for listening to the lesson, and I look forward to see you again. Bye for now.